The goal of this project was to design a glider which could travel the greatest distance after accelerating from a certain height. Our first step in the process was to look at nature and find inspiring examples of animals or insects performing similar missions, such as flying squirrels and stingrays. After analyzing their performances and what gave them these abilities, we decided that the driving factor in our design would be maximum area in order to obtain maximum lift. We used the code given to decide on a suitable motor for our glider. Initially, our calculations showed that wheel slipping might become an issue when using a high power motor. As this would have a negative effect on the performance of the glider, we chose a low power motor instead in combination with a 3.2 cm wheel. Nevertheless, after the first test it became obvious that with this motor, the glider would not be able to achieve any notable distance, which is why we decided to change back to a high power motor with 6000 RPM. The risk of wheel slipping was minimized by choosing rubber wheels with a profile, leading to increased grip on the takeoff ramp. During the prototype manufacturing process, we ran into several problems, which led to changes in the design. The initial positioning of the motor was not optimal, and we also realized a longer drivetrain would result in a better stability, which is why we changed the layout. We used a foam wing instead of a false band one, and also increased the height of the struts to allow for clearance for bigger gears. On the testing day, not everything went as planned. Even though the glider was driving in a straight line when pushed by hand, it became clear that the torque generated by the motor led to a turning during the acceleration phase, thus leading the glider to exit the ramp on the side and not using the full length of the ramp to reach its maximum speed. As this did not occur during the first tests, we were able to pin the source of this behavior down to the struts, which became loose and had too much clearance. With 2.2 meters, we missed our target distance by about 1 meter. Nevertheless, due to the quite strong curvature of the acceleration path, only half of the available distance on the ramp was used, and a day before the testing day, the glider reached 3 meters. Thorough analysis of the flight and the build phase resulted in a list of possible improvements as follows. A tailplane could be added to the design to stabilize the flight path and improve trimmability. Furthermore, the gear should be mounted in the center of the driven axis instead of the side in order to ensure symmetrical torque distribution and prevent the glider from turning to one side. This will also enable the use of carbon fiber rods on the front and the back axis, and reduce the weight by 6 grams. Spacers should be used to secure the axis in place instead of the tape used during the test. This will decrease friction and lead to a higher speed. The connection between the wing and the drivetrain should be improved to ease the change of the CG position, as well as access to the controller board for maintenance reasons. Precision during manufacturing and assembly should be improved as well, with closer fits to prevent the previous mentioned turning behavior. Last but not least, more testing, especially in optimal conditions, would have a great impact on the achieved result.